In this video, we will give a proof of my theorem for compact rank 1 symmetric spaces. And let me briefly remind my theorem and the proof for non-compact rank 1 symmetric spaces and Euclidean spaces. My theorem is about the shape optimization result for first Steklov-Dirichlet eigenvalue in two-point homogeneous space. We consider the domains bounded by two geodesic balls of given radii with a condition on the outer radius. This condition says that if ambient space is sphere, then the outer ball is included in a hemisphere. So if you give a Dirichlet boundary condition on the inner boundary and the Steklov boundary condition on the outer boundary, then the first eigenvalue has maximal value if two balls are concentric. In the second video, we give a proof for non-compact case in 4 steps. In the first step, we compute the first eigenfunction in a concentric annulus, which is B2 set minus the closure of B1. Using separation of variables, we can compute the first eigenfunction, and it is actually the real valued function A composite the distance function from the center of the two balls, C. And the real valued function A is defined by the integral of 1 over the density function from the inner radius R1 to R. From this identity, we can check that the first eigenfunction vanishes on the inner boundary. And the next step, we compare to the first eigenvalue of a concentric annulus and the first eigenvalue of an eccentric annulus, B2 prime z minus the closure of B1. Using our first eigenfunction in concentric annulus and the variational characterization of the first eigenvalue of an eccentric annulus, we can obtain an upper bound of the first eigenvalue of an eccentric annulus. Also, we can obtain the first eigenvalue of a concentric annulus by using the first eigenfunction of a concentric annulus. Then, to compare these two first eigenvalues, we will compare two numerators and the two denominators. This is step 3 and step 4. In the second video, we have shown the inequality in step 4 by using the idea of the proof of Newton's shell theorem. And this method is also applicable for our case. However, step 3 is not, so we only need to show that the inequality in step 3. In the second video, we note that the two integrands are equal, so we compare the value of the integrand in the different sets of two regions, which is B and B prime. So the important fact that we used is that the volume of B and B prime are same, and also our density function from C is increasing function in the distance from C. So So since the distance from C to a point in B is less than R2, and the distance from C to B prime is bigger than R2, so we can obtain this inequality. However, for compact rank-wise metric spaces, the density function is no longer increasing if R is bigger than the half of the injectivity radius of an ambient space. So the distance from C to B prime may have can be bigger than the half of the injectivity radius of the ambient space. So we cannot use this argument. So we need more delicate argument for step 3. So using this identity, our inequality becomes the following inequality, and we can obtain the following identity easily. Now we compute the right-hand side by using geodesic polar coordinate at the center of B2, which is C. Now let's define B sub RC by the geodesic ball of radius R centered at C, and we denote the distance from C to C prime by D. And also we define a map ANG sub C, which maps a point in ambient space without C to the direction from C to that point. Actually, the magnitude of the image of subset in M without C under this map is actually a kind of solid angle at C. Also, a point in the distance from C to a point in B ranges from R2 minus D to R2. Also, the distance from C to a point in B prime ranges from R2 to R2 plus D. So using geodesic polar coordinate at C, the right-hand side becomes the following identity, and also by using change of variables, we can obtain the following identity. Now, to show that the right-hand side is bigger than or equal to 0, we will show the volume of the former region is greater than the volume of the latter region. Also, we will show that the former integrand is bigger than the latter integrand. So the first claim says that if we denote A sub S by the subset in B2 without B2 prime contained in the geodesic sphere centered at C of radius R2 minus S. And also we can obtain A sub S prime be the subset of B2 prime without B2 contained in the geodesic sphere centered at C of radius R2 plus S. Then these two sets are depicted as in the picture. So the claim says the magnitude of the image of A sub S under ANG sub C is bigger than the magnitude of the image of A sub S prime under ANG sub C. If in three-dimensional Euclidean space, this inequality says that the solid angle of A sub S at C is bigger than the solid angle of A sub S prime at C. So to estimate the right-hand side, we consider a triangle C, C prime, S prime, which S prime is contained in A sub S prime. Then this set is this triangle has side lengths T, R2 plus S, and C prime S prime, which is less than or equal to R2, because S prime is contained in the ball B2 prime. In two-point homogeneous space, even though we know all side lengths of a triangle, we cannot obtain exact Riemannian angle of a vertex of a triangle. So to estimate this angle, we will use a triangle in constant curvature space. The constant curvature space, the constant curvature is defined is a real number k, which satisfies the radius of the hemisphere of the space form of k is R2. So the injectivity radius of the space form of k is smaller than the injectivity radius of the ambient space. So the k is bigger than the maximum of the sectional curvatures of M. Now in this space form of k, we consider triangles CK prime and SK prime, which has same side lengths of C prime S prime. Then by using triangle comparison theorem, the angle S prime C prime is smaller than the angle SK prime CK prime. And this is less than or equal to theta S, which is defined by the angle at CK of CK S sub S prime sub K CK prime, which has side lengths T, R2 plus S, and R2. So if we define A sub S prime sub K as follows, then the magnitude of the image of this set under ANG sub CK is the magnitude of this set divided by the density function of the space form of K at R2 plus S. So using triangle comparison theorem, our magnitude of the image of AS prime under ANG sub C is less than or equal to this quantity. So we obtain an upper bound of this magnitude. On the other hand, we can also define a subset in the space form of K, and we can obtain a lower bound of the magnitude of the image of A sub S under ANG sub C. So we will compare this lower bound and the previous upper bound, and this will gives our inequality for this magnitude and this magnitude. Since R2 is the radius of a hemisphere in space form of K, so the density function of the space form of K at R2 minus S has same value of the density function at R2 plus S. In addition, A sub S sub K is depicted as in the picture. So this is actually the image of the antipodal map of the A sub S prime sub K. So these two sets has same volume. Therefore, this lower bound and the previous upper bounds are same. So we can compare the two magnitudes of some set of AS and AS prime. So this gives the proof of the claim 1. Now we only need to show that the claim 2, and it is about the inequality for density function of ambient space. If ambient space is sphere of radius 1, the density function becomes sine r to the mth power. So the graph of the density function has a middle point at pi over 2, which is the half of the injectivity radius of ambient space. So our condition on the outer radius says that R2 is located in the left side of the middle point. So we can easily see that the value of the density function at R2 minus S has smaller value than the density function at R2 plus S. So this gives our inequality. For other compact rank 1 symmetric spaces, we can also obtain our desired inequality by simple computation. So this gives the proof of the claim 2. Therefore, claim 1 and claim 2 finishes our proof of the inequality in step 3. Oh, this is step 3. In my theorem, the theorem says that concentric annulus has maximal first eigenvalue among the domains bounded by two balls. So with Jiho-hong and Mi-kyung Im, we made a question that if we move our inner Dirichlet boundary to the outer ball, does the first eigenvalue decreases? And then for 2 or 3 dimensional Euclidean space, we did numerical experiment. We fixed the outer radius by 1, and we compute the first eigenvalue for various values of inner radius and the distances between the centers. Then our numerical experiment says the answer of our question is yes. However, we did not give an analytic proof of our question. One basic approach to prove our question is that showing that the differentiability of the first eigenvalue in T, which is the distance between the centers, and then computing the shape derivative of the first eigenvalue in T, and show that it is actually non-positive. Actually, we can compute the shape derivative of the first eigenvalue using normal derivative of the first eigenfunction in the inner boundary, but it is very difficult to analyze that term. For Dirichlet Laplacian eigenvalue problem, our question has been studied extensively. For Dirichlet Laplacian eigenvalue problem, the first eigenfunction vanishes on the boundary. So since the first eigenfunction is not sign changing in the interior, so we can say that the value of the first eigenfunction at a boundary point is always smaller than the value of the first eigenfunction at an interior point. However, in our case, we cannot say that fact, so we may need a new approach to tackle our problem. This is the end of my talk. Thank you.